Hello student, good morning to all of you. Students in class 11 physics, our today's topic is work energy theorem and momentum. Before we will learn about work energy theorem, I will just advise you about COVID-19 appropriate behavior. As we all know that the COVID-19 is still not ended. So we all need to follow these three rules. One is wear mask properly. Second, follow physical distancing whenever you are in the crowded place. And third, maintain hand hygiene. All the three rules are most important to protect yourself and your community by this COVID-19 virus. Okay, so whenever you are in the crowded place, you need to maintain minimum 6 feet distance by one another, and when you are out from your home for a very long time, so you need to maintain your hand hygiene by washing your hand or otherwise by using sanitizer. Thank you. So student, now we will start today's class, that is work energy theorem. Okay, so what is this work energy theorem? Here, work and energy, it means work done by a kind of energy is defined as work energy theorem. Okay, so let's we have an object of mass m initially at A, and by applying a force, that body of mass m is displaced by a distance or displacement s. Okay, now let's say initial velocity of the body is u and the final velocity is v after passes the time t. Okay, so according to this work energy theorem, the work done by the work done on a body is equal to the change of kinetic energy of the body. Okay, so let me write here, according to this theorem, work done by a net force in displacing a body is equal to change in kinetic energy of the body. Change in kinetic energy of the body. This is the statement of work energy, tells us about the work done by a net force to producing or to displacing it from point A to B is equal to given by the change in the kinetic energy. Okay, here if at point A the body have mass m and velocity is this, so we can say kinetic energy initial. This is, you all know that kinetic energy is half into product of mass and velocity. Here we have velocity is u, and for the second situation, that kinetic energy at B is half mv square. Okay, therefore according to the statement, the work done is equal to change of kinetic energy, change of kinetic energy. Okay, which means final energy, final kinetic energy minus initial kinetic energy. That means half mv square is equal to half mv square minus half mu square. This is ke final and this is ke initial. That thing is taken as change in kinetic energy and it is work done. Therefore work done is equal to kinetic energy, final kinetic energy and initial kinetic energy, or let's we see that this is the work energy theorem. Now we need to prove it, how it can be derived. Okay, now proof. Proof of work energy theorem. ठीक है? Now for proving work energy theorem, let's consider an object of mass m initially at rest with velocity u. After applying a force F equal to ma, by which it gets a final velocity v and displaces a distance s. Okay, so consider an object of mass m, initially at rest with velocity u equal to 0. Okay, now let due to a force F is equal to ma acting on it, force equal to ma, it displaces by a small distance s in direct s ds. Therefore small amount of work done by force is dW is equal to force into displacement, that is F into ds, and we have F is equal to ma ds. This is the small amount of work done. Okay, now student, we have here see, we can write A is equal to dV upon dt. Okay, for doing so, here this dW is equal to m dV upon dt into ds, by using value of A, dV upon dt. Now from here we can find that m ds upon dt into dV. This dt is taken in the order of ds upon dt, and student, here we have dW is equal to m and ds upon dt, that is rate of change of displacement, so we can say it v dV. This is the small amount of work done. Therefore this is your equation first. Total amount, total work by displacing from A to B. Okay, total work by displacing from A to B, that W is equal to, from A to B is dW. Here velocity at A is u and velocity at B is v, and the work done is equal to this quantity. From first we get it mv dV. Clear? So here this m is mass of the body, which is taken as common as constant. Then we get from here u v dV. Okay, here student, we have a formula for integration, that x dx is equal to x to the power n plus 1 upon n plus 1. Okay, so we can put here the same formula, that m, by using it, v square upon 2, and the limits from u to v. Here we can say this, if we have x dx, so we can prove it by using this x square upon 2. Okay, this is the simple formula of integration. Now by using the limit, we get half m v square minus u square. By multiplying inside, we get half mv square minus half mu square. Here student, this is that work done is equal to, this is in final kinetic energy, and after subtraction is initial kinetic energy. So it is equal to del Ke, and this is how we prove work energy theorem. Okay, complete it. Okay. Now from here we have two kinds of situation. That case 1, if K final kinetic energy is greater than initial kinetic energy, therefore we can say that del Ke, which means change in kinetic energy, is positive. Okay, that will gives that del K is positive, is the work done is equal to increase in kinetic energy. Okay, so first statement we have here, work done is equal to increase in kinetic energy. Okay, this is our first situation when the vehicle is at rest and by applying a force it gets an velocity v. So we observe here the final kinetic energy is maximum comparison to the initial kinetic energy. So the change in kinetic energy gives the result the work done is positive, which gives an idea that increase in kinetic energy by doing work applying that force. Okay, now second situation we have that this is cases first, and next we have second case, if K kinetic energy initial is greater than final kinetic energy, therefore change in kinetic energy is negative, which gives us work done is equal to del K equal to negative. Okay, this implies here first situation is this and second one is this. So this is gives an idea that work done is equal to decrease in kinetic energy. Decrease in kinetic energy. Okay, this is the work energy theorem, gives an idea which help us to do numerical based on it. Like a bullet is fired from a gun and after traveling a certain distance or after traveling with a certain velocity hits a block and penetrate in the block by a displacement, let's say 5 centimeter, 7 centimeter, 8 centimeter, etc., and then stop. So you have the initial velocity that the bullet is fired from the gun, and another one is the final velocity, which is bullet stop by the block. Okay, so in that case initial velocity is higher comparison to the final velocity. So here two things are there. Final velocity is to penetrate by a 5 or 10 centimeter inside the block, and after that it will be stopped. So the work done by the bullet after hitting and traveling a distance in the time of penetration inside the block by 5 or 10 centimeter. So you can calculate from here the potential energy, and that potential energy equal to the kinetic energy by which the bullet is fired. So in this case you can calculate kinetic energy half mv square is equal to potential energy, that is mgh. You can do these kind of calculation for solving your numericals. We will take some numerical based on the work energy theorem. Just note down it. Now we understood about concept of momentum and energy. So between energy and momentum. Energy and momentum of a body. Okay, students? So, if you have the idea related to energy and momentum, here, student, it is very clear. If we have to relate the energy with the momentum, that means both the things are related to the object in motion. Object in motion. First condition for relating it, that is the object is in motion. So if the object is in motion, so here we discuss about the energy. It is basically which kind of energy? So answer is, it is basically kinetic energy. And just you learn about how much is the kinetic energy of a body if that particle is moving. So this is equal to half mv square. It is clear or not? So if you know about this and you have the value of momentum P is equal to mv. So by multiplying here m and divide m in the kinetic energy, what we get? Let's see. Kinetic energy. For kinetic energy we can use only the symbol K. Okay, so when we divide the kinetic energy m v square by m and multiply also by m, then we get that result is equal to half m square v square upon m. From here we can say that 2m is equal to 2m into mv square. Now student, here we have the relation of momentum. So we can put here that k is equal to half upon 2m is equal to p square. This is the initial relation with kinetic energy. Now we can relate from here three conditions. Here by doing so, for energy, for kinetic energy, let's say first point. Okay, so when we correlate the kinetic energy with the momentum, first we get from here the kinetic energy is directly proportional to p square. Clear or not? Okay, when you compare it like this, so you can also say the momentum is inversely proportional to square root of k, or we say kinetic energy. It will be done or not? So this is your first relation for correlating the energy and momentum as per given situation in the numericals. So now second situation is kinetic energy is inversely proportional to the mass of the object. So from here you can also say mass is inversely proportional to the kinetic energy. Just find it very quickly. Okay, now see here, this is by this simple rule. Now we calculate from here the value of momentum p square is equal to 2mk. Okay, so the momentum is equal to under root of 2mk. Clear? Therefore by this relation we can conclude from here, first condition is P is inversely proportional to the kinetic energy, and also P is inversely proportional to the mass of the object. When we correlate momentum and energy, you need to follow this rule, not this. Okay. Now we can understood about some graph based on the concept. This gives mass, this gives momentum. So this gives kinetic energy. So we have a graph like this. This is for P is constant. Okay. Second situation is this gives momentum, this gives mass. Therefore, that situation in this, by this graph we can say, because we are not using here the kinetic energy in the x or y axis, therefore here kinetic energy is constant. Okay. And the last condition is for momentum and kinetic energy. By this we say mass is constant. Okay. These are the graphs which we get from the relation between kinetic energy and the momentum. Let's we take one problem which is based on the relation between kinetic energy and momentum. So the linear momentum of a body is increased by 10%. What is the percentage of its kinetic energy? Okay, so here we have the linear momentum increased by 10%. Okay, let the object at point A have momentum P, let's see 100. Okay, and when it reached at point B, its momentum is increased by 10%, which is 110. Okay, it is very simple. So you can calculate from here the change in momentum. Okay, so by using this you can also say P1 100 plus 10 upon 100 for calculating percentage. This term can also be used. P1 increased by 10%. For solving this, we use this condition. So from here we calculate the ratio of P2 upon P1 is equal to 110 upon 100, from which we get P2 upon P1 is equal to 11 upon 10. Clear? This. Now, because the mass of the body here is m and here is also m, therefore initial velocity is v1 and final velocity is v2. Therefore, by using the values mv2 upon mv1, you will calculate from here 11 by 10. Here m cancel by each other, and you will get from here that v2 upon v1 is equal to 11 by 10. Is this clear to all of you? Now, initial kinetic energy, we have half mv1 square, and final kinetic energy, let me say E2 is half mv2 square. Therefore, ratio of initial and final energy, or we say E2 upon E1. This we get from here half mv2 square upon half mv1 square. From here half cancel, half m is cancel, and we get v2 upon v1 square. From here you will calculate that 11 by 10 square is 121 upon 100. This is the energy. E2 upon E1 is equal to 121 upon 100. This is energies. Therefore, change in kinetic energy, which is final energy minus initial energy. Okay, from here this we say E2 in our question, and this is E1. So you will calculate common from here E1. You will find that E2 upon E1 minus 1. Okay, so this is equal to E1, and this will 121 upon 100 minus 1. From here you calculate that change in kinetic energy is 21 E upon 100. Okay, now percentage of change in kinetic energy, which is del Ke upon initial energy, which you get from here into 100. From here you will find that 21 E upon 100 into 100 and divided by E1. This E1 is cancelled, 100 is also cancelled. then you will get 21%. Okay, therefore change in kinetic energy by doing so is 21%, and this is increased. Okay, so note down this, and thank you.